Hello. We've got a big one today. The limit definition of a derivative, right? So we briefly talked about the limit definition of a derivative, meaning the difference quotient, really. Talked about that in our last video, right? But today we're going to go in depth. There are a lot of things we need to cover, some pretty important things. This will carry out through the rest of calculus, this basic idea, right? Now I have it written there. The limit definition of a derivative isn't really all that tough. It's just the limit as the delta x, or change in x, approaches 0 of our difference quotient that we talked about in the last video. So if you haven't seen that video, you should go watch it. It's pretty important, right? We'll need to know the difference quotient for today. So as a kind of overview, to introduce the limit definition of a derivative, we're going to go over some simple examples, and you'll start to see patterns, right? It's not all that tough. Everything that we've already been doing still applies. Limit laws, how to analytically solve a limit, some tricks that we went over in the past, right? Those still apply. And we'll use some of those today. You'll see that, right? I'm going to choose a simple function first. Let's say f of x equals x to the fourth, right? And I wrote that there. Sorry, yeah. F of x equals x to the fourth. So now, if I were to write out the difference quotient for that, it'd be f of x plus h minus f of x over h. Oh, and sorry, I just said h there. H is another very common variable. A lot of people will use, a lot of teachers you'll see. Delta x and h are interchangeable, right? We use h to describe our change in x all the time. I just like to use delta x because I believe it represents the change in x more clearly, whereas h can kind of be confusing at times, right? So I'll still use delta x, but if you hear me say h, just know they're the same thing, right? So let's write out our difference quotient. That's going to be x minus, when we are doing f of x plus delta x, we are trying to find what f of x plus delta x is, right? We're inputting that to our function like if we were to plug in 1 or 2 or 3, right? So let's do that. F of x plus delta x is going to be x plus delta x to the fourth. So do you understand how I got that? Because that's pretty important, right? Where there's an x, I plug in x plus delta x. So x to the fourth becomes x plus delta x to the fourth, right? Now, minus x to the fourth. You know what? Actually, now that I think about it, this is going to get pretty messy. So let's say f of x equals x squared. That'll be much easier, and you'll see why here in a second, right? And we're going to put all of that over delta x, right? That's our difference quotient. Sorry if the light's kind of in the way. That says, in parentheses, quantity, x plus delta x squared minus x squared, just our f of x, over delta x, right? And now what we're going to do is I'm going to take the limit as delta x approaches 0 of this function here, this new difference quotient. Now, if you can't see that, I'll bring that in. The light is always in the way. All right. See that? That's the limit we're going to be doing right there. You'll set up that limit a lot of times if you work on problems like this. So, as always with limits, the first thing we're going to do is we're just going to try to plug in delta x equals 0. We're going to see what happens, right? We get x plus 0 squared minus x squared over 0. You can probably already tell some bad stuff's going to happen, right? I'll write this in red because we can't do this. We're going to get x squared minus x squared over 0. And that's going to be 0 over 0 in indeterminate form, right? So I'm just going to cross that out because that's not mathematically true. We have some more work to do, right? Now first I'll solve this in kind of the standard way you'll see. So I'll rewrite this down here, right? Limit as delta x approaches 0 of x plus delta x squared minus x squared all over delta x. All right, now, can't see that because the light's in the way. Again, there that is, right? So delta x approaches 0 of our difference quotient. Now, what I'm going to do is I'm going to try to simplify this, right? Like we did in our example with the hole in it. If you remember that, that notes example kind of a long time ago where I solved that on a piece of paper, right? The same thing applies here. We're going to do a very similar thing, right? Remember, we don't remove the limit notation until we plug in delta x equals 0. We do not get rid of that limit notation because we are still taking the limit. We did not evaluate, or we have not evaluated this limit yet. So, and this is why I switched our function to x squared instead of x to the fourth. We're going to FOIL this, right? And I don't want to use any Pascal's triangle rules to make that pretty messy. It's going to get bad pretty fast. So we're just going to FOIL this out, right? And I'll just do this over to the side here. Let's go over here, right? So that's going to be x plus delta x times x plus delta x, right? And I like to do these FOILs out by hand. That's going to be x squared plus 2x delta x plus delta x squared, right? Did I just do that right? I believe so, right? There's my algebra on that. Okay. So let's put that back in. We have x squared plus 2x delta x. X and delta x are different variables. We cannot combine those. Plus delta x squared. And that's not changing x squared. That'd be more delta x as a variable squared. So my bad, I probably should put that in parentheses to be a bit less confusing. That is delta x quantity squared. And then minus x squared over delta x. And now, right, we see here, x squared minus x squared, it's going to cancel out. It's going to be 0, right? And if you do this correctly in every single one of these problems, if you're dealing with like basic polynomials, right, like x squared, x to the fourth, 3x cubed, stuff like that, all of your terms without delta x should cancel out. And that's going to help a lot because that's going to let us rewrite this as the limit as delta x approaches 0 of 2x delta x plus delta x quantity squared and all over delta x. So still cannot plug that in yet, right? Can't plug in delta x equals 0 because there's delta x in our denominator and that's all. So it's just going to be over 0 and we can't do that. We're not going to get a real answer for this limit, right? So I'm going to simplify this once more. Well, I'll do it in 2 steps. Limit as delta x goes to 0 of, and I'm going to factor out delta x, and you'll see why here in a second. It's going to let us cancel some stuff. It's going to be delta x times 2x plus delta x, right? If I were to FOIL this out, we'd get 2x delta x plus delta x squared, right? Over delta x in our limit. And so delta x will divide out and cancel with delta x, right? And now, as our final limit, oh, that was an embarrassing equal sign right there. My apologies. Limit as delta x approaches 0 of just 2x plus delta x. And I'm kind of overlapping here, so I'll actually rewrite that because this is our final expression. It's pretty important, right? How about over here, right? That's going to be the limit as delta x approaches 0 of 2x plus delta x. Boom. This is our final simplified answer, or limit expression, right? We can plug in delta x equals 0 now, and we just get that equals 2x, right? That equals 2x. And I'll bring the phone over here so you can see all my math. I'd like to take a picture of this or pause real quick. All right, and then I'll go over here to the final simplified limit, we get 2x as an answer, right? All right. And now, remember back to our limit laws video. Remember how I said that we will use the limit laws without even thinking about them, right? We did that here multiple times. At the very beginning, when I plugged in delta x equals 0, we kind of used the limit law there. Maybe you could argue we used the quotient rule or quotient law and the difference sum law, right, in that numerator and denominator. But over here, you could split this up into the limit as delta x approaches 0 of 2x plus that same limit of delta x. And really what that get you is 0 for this delta x limit term plus, and then since there are no delta x terms in 2x, you don't really do anything, right? And so you get 2x, and you'll start to see a pattern here. If I were to do f of x, right, if I were to go all the way back and say f of x equals x to the 4th, I can tell you because I don't know about you, I've done my fair share of calculus. That's why I'm here right now teaching this, right? I'd like to share all this knowledge with you guys. I can tell you right now that if we were to do this whole limit of the difference quotient for this function here, we're going to get 4x cubed. And we'll learn some tricks in our next few videos about how we can kind of skip all of this, right? Because this is a lot of work, a lot of algebra, and sometimes there's some trial and error. If we did a much more complicated function, something that maybe wasn't a polynomial function, right? Like what if we did a rational function, like 3 over x squared, right? Or just 1 over x, for example. Any rational function, that could get pretty messy pretty quick. Or if we did a function raised to the power of a fraction, right? So if we did like a root function, x to the 1/2 or the square root of x, it get pretty tough pretty fast. And in those examples, you're going to have to use some algebra tricks to rationalize, if you've heard of that. That's not as important as you go further in math. We really don't care if you rationalize denominators or not. If you have those rational functions, though, you will have to do some algebra, some multiplying top and bottom, numerator, denominator, by some certain values to kind of cancel out fractions, right? And I'll upload some example videos going over more challenging difference quotients. But really, in our next few videos covering content, we'll go over some of these derivative rules, right? That cut out all of this work and let us skip right to the answer pretty much. That being said, there's one more time in the future where we're going to have to do more stuff with limits. For the most part in calculus, though, we do these limits behind the scenes. I didn't do this. I did not do all of this algebra in my head. I used a trick that follows patterns that we will see in these limits, right? So I will release a few videos so you can see those patterns, right? All right, let's look at all of this. The limit definition of a derivative. It's a pretty tough concept at first, but it'll get easier, I promise. And as in last video, let's go over kind of what we're doing here, right? Have a graph of x versus f of x. Ooh, here. I'll even show you what we just did. This would be like the right side of that function, right? What I did is, and I'll pick points, because we're not picking any ordered pairs in our limit definition of derivative problems, but just to make this a bit easier, I'll pick some points. Now if we draw a line through those, the difference quotient on its own will find the slope of that line between those points, right? Now what the limit is doing is taking this delta x distance and it's decreasing it. We're approaching 0, right? We are getting really, really close. We are pushing these two ordered pairs together, right? But, and again, as I said in the last video, we're not using numbers in our difference quotient. We're using whole functions. We're plugging in f of x. and f of x plus delta x, right? Those are expressions, those aren't numbers. And our derivative ended up not being a number. It ended up being another expression, right? And sometimes you'll do derivatives and you will get just numbers, but you see we get another whole function, right? So the limit definition of a derivative, right, with our difference quotient allows us to find the slope at any point, right? So what I could do now with this derivative is I can plug in any x value from this original f of x point, and I can find the slope at that point, right? And down the road, we'll go down, we will cover another limit derivative kind of thing where we skip all of this and go straight to a number. Like if I were to, instead of finding a function and then plugging in a number, we do some limit stuff, some calculus, and then we just get a slope, we get an answer. But yeah, our difference quotient, our limit definition of a derivative, that lets us find slope anywhere, right? I could find the slope at x equals 10,000. It'd just be x equals, or it'd be, the slope would equal 20,000, right? If I plugged in 10,000 there. Yeah. We get sort of a tangent slope, right? And again, as I said in the last video, please, as you take other classes, think about what's happening, right? Slopes happen everywhere. Slopes are everywhere. Continuous change is everywhere, right? And derivatives help us find slope. Trying to think of an example of maybe, the chemistry ones are pretty complicated. In physics, though, if you're driving a car, right, you see that miles per hour on your speedometer there, right? What that's doing is it's doing calculus. It's doing some calculus stuff to figure that out. You have an acceleration, a velocity. It's finding your change in position, really, right? Like if I had a position function for where your car is at any point, it could be here. Your car could be here, right? And now your car is finding your change in position, your velocity, by basically doing a bunch of this calculus stuff, and then it's plugging in a number and it gets 34 miles per hour, right? So calculus is everywhere. Anyways, I hope you enjoy. I'll come out with some videos here soon covering more difficult topics, but I hope this is a pretty good introduction to the limit definition of a derivative. This is a very, very important topic in calculus. Derivatives are like half of calculus, I promise. We'll be using derivatives for forever. So, anyways, goodbye class. Thank you for learning with me. I'll see you in the next video. Goodbye.